In this video, we will discuss how to calculate the band gap energy with baseline correction using torque plot from UV-Vis absorbance data in Origin. A misuse of the torque plot to determine the band gap energy may lead to erroneous estimates. We know that the band gap energy is the energy needed to excite an electron from the valence band to the conduction band. This is important as an accurate determination of the band gap energy is crucial in predicting photophysical, photochemical, and photocatalytic properties. A glimpse from the history reveals that in 1966 Stark proposed a method for estimating the band gap energy of amorphous semiconductors using optical absorption spectra. His proposal was further developed by Davis and Mott. In this video, I have explained in detail how to calculate the band gap energy from UV-Vis absorption data using torque plot. However, it is of utmost importance to know that this approach can be applied for all semiconducting materials that do not absorb light and the sub-band gap energy. Such materials must be the pristine, undoped, or defect-free amorphous semiconducting materials. It is vital to note that when it is applied to materials showing a considerable absorbance at energies below the band gap energy, the obtained results may be significantly distorted. The baseline correction must be made for defected, doped, bulk, or surface modified materials. All these modifications may introduce intra-band states that reflect in the absorption spectrum as an Urbach tail, that is, an additional broad absorption band. Its presence influences the torque plot and therefore must be considered to determine the band gap energy. In such cases, a direct application of the torque method results in an inaccurate estimation of the band gap. This error appears frequently in several publications in which authors incorrectly interpret the shift of the x-axis intersection point to lower values as reducing the band gap energy. In fact, the apparent reduction in the band gap energy is due to the inapplicability of the torque method in such cases. To prove this claim, the reference article with references therein explains such cases in detail. This is the original TiO2, which is an indirect band gap material with a magnitude of 3.22 electron volt. When titania is modified with a dye, etc., intra-band gap states are incorporated. This caused the band gap energy smaller than that found for the original titania sample. Here we will consider the intra-band region as a baseline and need not to drag it to the y=0 axis. And here some other spectra of the same, which clearly shows modification in the structure and the eventual incorporation of the sub-band gap energy states. Thanks for watching the video.